The last couple of days, we've talked about momentum. Momentum is the product of an object's mass and velocity at a specific moment. Now, we've solved for momentum when the velocity was constant, and we've also solved for the momentum after an acceleration. But what those two questions have in common with each other is that they're both finding the momentum at a specific moment in time. But momentum changes. As we saw, that momentum changes after an acceleration. We didn't quantify that. We just saw for the final momentum. Today, what we're going to do is quantify that. What is the change in the momentum? What significance does the change in the momentum have rather than just the momentum final or the momentum initial? We're going to define a new term called impulse. It's defined as the change in momentum, the gain or the loss of momentum experienced by an object. Impulse is a vector. Of course it's a vector. It's change in momentum. Momentum's a vector. Velocity is a vector, therefore momentum's a vector. Momentum's a vector, therefore impulse is a vector. Impulse is a vector. It can be a positive value or a negative value. We're going to say that it's positive when momentum is gained in the positive direction, or we could say or lost in the negative direction. Think about that for a second here. Just drop the pens for a second and just listen, and then I'll give you a chance to write this, okay? Impulse is positive when momentum is gained in the positive direction or lost in the negative direction. Okay, think about this. You've got, this is to the right, right? Look over there, that's right. That's the positive direction. I'm not moving. As I speed up in the positive direction, I'm gaining momentum in the positive direction, right? That's a positive impulse. When else could I get a positive impulse? Well, maybe I'm going that way. Maybe I'm going left in the negative direction. I'm going in the negative direction, but now I'm slowing down. If I'm gaining momentum to the right, or if I'm losing momentum to the left, those are both positive impulses. Make sense? The impulse is to the right in both cases. Now, on the other hand, and again, I'll let you copy this in just a second here after I finish this little thought here. We can have a negative impulse whenever we lose momentum in the positive direction. So I'm moving to the right, but I'm slowing down to the right. That's a negative impulse, a loss of momentum, right? In the positive direction. But I can have a negative impulse as well when what do I want to put in brackets there in blue? Somebody's kind of whispering it. Jade, you got it?
Increase in momentum in the negative direction.
Yeah. Or you gain momentum in the negative direction. Picture this for a second, okay? I got a rock that's falling. As it falls, it gains momentum, right? But it gains momentum downward. That would be a what? Positive or negative impulse? What is it? Negative, right? That would be negative. When it hits the ground, it stops. It slows down and stops when it hits the ground, right? It's moving downward, but it slows down. That would be a positive impulse. When I throw the rock up into the air, it's going upwards, but slowing down. That would be a negative impulse because I'm losing momentum in the positive direction. Does that make sense? Okay, now I'll give you a chance to copy that down. How many of you guys remember Newton's laws? Newton's first law, object in motion stays in motion in a straight line. Object at rest stays at rest. We kind of talked about that a little bit with inertia yesterday, right? Third law, object A applies a force on object B. Object B applies an equal, somebody said it, and opposite force on object A. Second law is just pretty much F is equal to M times A. It's phrased a little bit differently usually, but that's what it boils down to. F is equal to M times A. But here's what I want to do. I want to replace A with delta V over delta T. It's like the second equation we learned in Physics 20. A is equal to delta V over delta T. And then I just want to rearrange that. T's on the bottom. I want to take the T up by multiplying. I get F times delta T is equal to M times delta V. What's M times V? What's M times V? Not M times delta V. What's MV? Easy question. What's MV? What's it mean? The product of mass and velocity is momentum. All right, well, what's M times delta V then? MV is momentum. M change in V is change in momentum, right? So M times delta V is a change in momentum. We define the change in momentum as the impulse. So impulse is equal to M times delta V, but you can see it's also equal to F times delta T. Which should make sense if we think about that. What do you got to do to change the momentum of something? This desk has zero momentum. How do I give it momentum? I got to apply a force on it. I got to push it. And the longer I apply that force for, the more the change in momentum is. F times T is equal to the change in momentum, as is M times delta V. The units that we use here, mass, of course, is kilograms. Delta V, be careful with this, okay? A lot of people forget to put the delta in there. That's really important for your sake to put the delta in there. If you don't put the delta in there, what's probably going to happen is you're going to forget one of the velocities and only include one. And you're going to get it wrong. Delta V is in meters per second. So impulse could be kilograms meters per second. T is in seconds. F is in newtons. So delta P could also be newtons times seconds. Exactly the same thing. At this point, you can use whichever one you want. Now, finally, there's a reason that I put this in red right here. If you look at your data sheet says F times delta T is equal to M times delta V. It doesn't say delta P. We've got to write that in ourselves. Delta P, the impulse, measured in newton seconds or kilograms meters per second, is equal to F times T and also equal to M times delta V. But we got to kind of remember that because it doesn't say delta P or impulse on our data sheet. Now we're going to do a problem right now. That's going to end it for us for today. Tomorrow we're going to learn some of the qualitative implications of impulse. What does this mean? Okay, we can calculate force or calculate delta V or calculate the impulse, whatever, but what does it really mean to us in an everyday world? Okay, what's the significance of impulse? And there are some pretty important implications of this. But again, that's coming tomorrow. Right now we'll just focus on doing a problem. Example number 1. It says a 1,200 kilogram car is originally traveling at 25 to the north. 35 seconds later, it's traveling at 10 to the south. I want to circle this because if I don't, probably what am I going to do? Forget to make one negative, right? I'm telling you right now, you're going to have 5 multiple choice unit tests. You're going to have 3 written response unit tests. Your first written response unit test involves a problem where there's a north and a south in the same problem. And I would say about 20 to 25% of people forget to make the south negative. Okay, I'm telling you right now, your first written response test, look around you, and of every 5 people around you, there's going to be 1 to 2 people that forget to include the negative for the south. Okay, don't let it be you. Okay, let it be the person beside you, not you. Determine the impulse experienced by the car over 35 seconds. All right, let's write down some givens here. We've got a mass here that's 1,200 kilograms. We've got a VI that is 25.0 meters per second. And we've got a VF that is 10 meters per second. We've got a time here that's 35 seconds. And we want to find the impulse. Is that all right? Usually when I ask that question, Usually it's not. What small mistake? Small but important. Small but critical mistake did I make, Erica? Yeah, the 10's got to be negative, right? That's why we circled south in red, so we wouldn't forget that. Now, look, we know that impulse delta P is equal to F times T, and it's also equal to M times delta V. We know we're going to use this part. What other part do you want to use? It should be pretty obvious to us, right? F times T or M times delta V? You know what F is? You know what T is, right? But you don't know what F is. You know what M and you know what delta V is, so let's go with that. Let's say delta P is equal to 1200 times delta V, VF minus VI. Negative 10 minus 25. Negative 10 minus 25. So we're going to say 1200 times negative 35. Gives us a value of negative 42,000. That's a negative impulse. Why is it negative? Should it be negative? I was going 25. Look, that's north. Okay, that's towards Calgary right there. I'm going at 25 to the north. Okay, this is me walking 25 to the north, walking really fast, 25 meters per second to the north. But what happens? I slow down, going to the north, I stop, and then I change direction, and I end up going 10 meters per second to the south. When I was going to the north, I was slowing down. That's a negative impulse. When I was going to the south, I was speeding up. That's a negative impulse. So of course it should be negative, right? The elegance of mathematics. It works out. And if we're consistent with our science to the problem, our answer is the sign that it's supposed to be. Okay, finally, B. It says, what's the force required to change the car's velocity from its initial value to its final value? Let's this time use the F times T part of it. We already have the impulse. We divide that by the time we get the force. I'm saying negative 4.20 times 10 to the 4. And we divide that by the time of 35 seconds, 35.0 seconds. We do that, we get negative 1200. Or negative 1.20 times 10 to the 3 newtons. I was going north and I slowed down. Which way is the force? South. I was going south and I sped up. Which way is the force? South. Of course it's a negative force. Again, the elegance of it all, right? If you're consistent through the problem, it just works out the way that it's supposed to work out. Here's what I'd like you to do now. Hopefully you finish this up in the next 15 minutes. If you don't, you're going to finish it up for homework, but there's a pretty decent chance you will finish it up in class here. Please take a look now at worksheet number 2. I would like you by tomorrow to have the first 6 questions done on worksheet number 2.